Good afternoon and welcome to this dissertation defense. My name is Dr. Shireen Snelson and I'm the graduate faculty representative for this defense. This means I'm not a voting member of the defense committee. Instead, I'm here to make sure the defense follows graduate college guidelines. To begin, I'll ask everyone to please remain muted unless you're speaking, and if you are speaking, please make sure that your cell phones and other electronic devices are turned off or silenced. There are several parts to this defense. A presentation by the student that will run up to an hour. At the end of the presentation, there will be time for members of the audience, the public audience, to ask questions. When the questions are done, I'll ask the audience to leave so that the defense committee can have a private session with the student. So normally the committee will hold questions until that time. When that's done, I'll ask the student to leave so that the committee can discuss the defense. And with that introduction, I'd like to introduce Dr. Wright, who is the committee chair, and he will introduce the student and the rest of the committee.
Thank you, Shireen. So for those who don't know me, I'm Grady Wright. I'm a professor in the math department, and it's my pleasure to serve as the supervisor of Kathryn Drake's PhD thesis. So Kathryn received her her undergraduate degree from Northwest Nazarene here in Idaho, and then joined Boise State for a master's degree. Which she did under my supervision as well, and finished in 2017. And then I was fortunate enough that she wanted to stay on here at Boise State and be one of the first students admitted to the PhD in computing program in the computational science and engineering emphasis area. And I was very happy that she wanted to work with me, and even happier that she was able to get funding through several very nice programs. The first being the NASA Idaho Space Grant Consortium, and that was supported her in her first year. And then the second is the Department of Defense, which is a very nice program that Kathryn was accepted into through the SMART Fellowship. So, so I can't wait to hear her talk today, but before I turn it over to her, let me introduce the rest of the committee. So as a second committee member is Professor Jody Mead, who's also in the math department and co-chair of the PhD in computing program. And then Min Lon, who's in the computer science department with a physics background, computational physics. So, so we should be hearing a little bit about computational physics today also, and computational math and computational science. So hopefully everyone will enjoy the presentation. And with that, I think it's my turn to turn it over to Kathryn, unless Shireen needed to say something else.
We can go ahead. I look forward to hearing your talk, Kathryn.
Thank you. Just to confirm, can you hear me? Grady, can you confirm you can hear me? Okay. Maybe.
No, we could hear you. He was nodding.
Okay. Oh, okay. All right. All right. Well, everyone, thank you for coming and being here virtually, as it ended up being. My name is Kathryn Drake, and I'm going to be defending my dissertation today. The title, as you can read, and I will now read for you, it's a collection of fast algorithms for scalar and vector value data on irregular domains, spherical harmonic analysis, divergence-free, curl-free radial basis functions, and implicit surface reconstruction. And the presentation is even longer than that, so strap in. Okay, a brief outline of what I will be covering today is I'll start with an introduction, introducing the three papers in this dissertation. So my dissertation is composed of three papers that cover three different methods that we've developed. So I will introduce those, and in each of the papers, I will talk about the motivation and background of what prompted us to come up with these project ideas, what we contributed to the field and to the literature, and then I'll finish with some numerical results. And then I'll end the presentation with concluding remarks and notes on future work. Okay, so as I said, this dissertation is composed of 3 papers that address applications that arise in a variety of fields. So we have cosmology, we have geophysics, electromagnetics, and even graphic design. And while these fields all seem disparate at first, they have this commonality in that they have large scattered data sets, they are on irregular surfaces, they deal with regular surfaces, and they need fast and accurate computations. So that is the thread that's holding all of these projects together, and that's like the main thesis of this dissertation. So the first paper that I'll be covering is titled A Fast and Accurate Algorithm for Spherical Harmonic Analysis on HealPix Grids with Applications to the Cosmic Microwave Background Radiation. And it was accepted and published in the Journal of Computational Physics earlier this year. So the motivation for this paper is the cosmic microwave background radiation, which I'll be referring to as the CMB. So what is it? It is relic radiation left over from the Big Bang. When it was discovered in the 1960s, it was actually discovered on accident. As the word says, it is this faint microwave radiation that's kind of buzzing in the background of everything that we detect in the sky. And it's the most perfect black body ever measured in nature. And what this means is that it has almost an exactly uniform temperature all over, except for there are tiny temperature differences on one part in about 10,000. So the map that you see here, this blue, green, and red map, this is actually a map of the CMB temperature differences. And these temperatures are what actually can give us insight to what was happening when the universe was forming. Well, how does it do that? Well, first, I just want to briefly, very generally explain what these temperature differences represent. So right after the Big Bang, the entire universe was very, very hot and dense, and it was called a plasma. So we call this photon baryon plasma, if you will. And what happened is once gravity started having an effect, it would pull this plasma into these gravitational wells. So that's what's depicted here. And the system kind of mimicked this system of like balls on a spring, which we're very familiar with. So the matter would collect into the gravitational wells and pressure would increase. And as pressure increased, temperature would increase. And so they would come together, it would get very hot, the pressure would increase until the pressure would overcome the gravity pull, and then it would push back out. And then it would pull back in and push back out. And it created these oscillations. So these oscillations in pressure and thus temperature are what actually caused the peaks in what's called the CMB angular power spectrum. So this is what the angular power spectrum for a CMB temperature map looks like. And this is what we're focusing on in our project. So again, the extrema and the oscillations become these peaks, and these peaks are what give us insight to cosmological parameters for our current model of the makeup of the universe. So for example, the confirmation of the first peak told us that our universe is spatially flat. And then if we can confirm the second and third peaks, it will give us insight to the amount of dark matter and the amount of regular matter, which is in the universe, which is a really big topic in cosmology. We currently don't know a lot about dark matter, so that's why this is such a big area of interest. And something that I want to note here, this L, hopefully you can see my mouse, this L here is a function of angular scale in the sky. So the higher the L, the smaller the amount of the sky that you're looking at. And as I said, the second and third peaks right here, this is what we really care about. This is what we want to get refined analysis of. And it's important that we notice that these are at relatively high L. So this is also something that was important to us when developing our method. We wanted to be able to find a fast and accurate way to calculate this angular power spectrum while focusing on these values at higher L. How is this thing calculated? Well, it's calculated using spherical harmonic coefficients, which we will be denoting ALM. So these spherical harmonic coefficients are what we really honed in on in our method. In order to see how our method performed, we had to compare it to the current method that is being used, which is used by NASA, and it's called the Hierarchical Equal Area isoLatitude Pixelation. Say that 5 times fast. We're going to be calling that HealPix Grid. So the HealPix Grid is what NASA uses to collect the CMB temperature maps. So I want to describe what that actually looks like, what this grid is, how it's defined. So the resolution of the grid is defined by this parameter that we will be calling n side. And n side actually divides each base pixel into n squared pixels. So as you can see here, what I have shown is the set of base pixels. There's 12 on the sphere. And then notice for n side equal 2, as you can see, it splits, for example, let's look at this pixel, splits it into 2 squared or 4 equal area pixels. And then so on, you can see 16 and then 64. I almost said 84, but I know math. So n side is the parameter which helps HealPix define the resolution. And just as a note, when collecting data on the CMB maps, they have a very high n side, a very high resolution, something like 12 or 13. So a lot of pixels here. And what we'll be calling the centers of these pixels, we will be calling those the data points. So a HealPix map has 12 times n side squared pixels, and also as a result, 12 times n side squared data points. Okay, so this is what it looks like on the sphere, but in order to get an idea of what we were going for with our paper, I want to map this HealPix grid, for an example with n side 4, map this grid to a latitude-longitude grid. We're used to seeing that with maps of the Earth, so it's the same idea here. And what you'll notice is that it's split up into regions, as you can see by color. So there's a northern region in blue, an equatorial region in red, and then a southern region here in, I think, like gold, orange, yellow color. And something to note is that you can kind of see it in the grid. These points are split into rings of constant latitude. So they are equally spaced in these rings of latitude. So HealPix is also the name of the software that NASA uses to calculate the angular power spectrum of CMB maps, and thus the spherical harmonic coefficients. But what they use is actually a low order approximation to the inner product, as shown here. And they try to improve that approximation using iterative schemes, pixel weights where they put different weights on the pixels, ring weights where they put different weights on the rings. That has a disadvantage. It does not offer optimal complexity specifically for spherical harmonic analysis. We've actually shown in our paper that it's order n3 to the 3 halves. And even more than that, the Jacobi iteration that's used in the default of the HealPix software does add to the computational cost. So for our method, what we wanted to do was to find a way to compute these spherical harmonic coefficients in a way that lends itself well to using spherical harmonic analysis. Specifically, we're going to be using a fast spherical harmonic transform. So the first thing that we really wanted to do was get a more uniform grid. So we take the HealPix grid shown here on the left, and we use Fourier analysis to upsample it so that all of the rings of latitude have the same number of points. And just something that's important, the nodes are now all equally spaced in latitude, and there's the same number on each ring. And even though it might look like it, oh, I'm sorry, equally spaced in longitude. And then they're unequally spaced in latitude. So they're equally spaced in this way, but they are unequally spaced in this way, which will affect the method that we have to use later. Now, something that's important for data collected on a sphere, like for the CMB data, is that it is biperiodic. So much to the disappointment of, I'm sure, some people, the Earth is actually a sphere. And if you go in north-south, you will just keep going in this repeated nature. You know, you'll start at the North Pole, you'll go down to the South Pole, and so on. Similarly, if you go east-west, you will keep going back to where you started if you stay in that same line of latitude and longitude. This is called biperiodicity. So if we map the Earth, for example, in this picture down here at the bottom, if we map the Earth to a latitude-longitude grid, it does not preserve biperiodicity in the latitude direction. So notice if we go this way, we restart back in Africa, but if you were to start in Antarctica and go up here to Russia, you would then fall back into Antarctica, which is not exactly what happens on the actual globe. So in order to ameliorate that, we have to use something called the double Fourier sphere method, which is a way to, you do this flip and shift of the data, and then that way it is preserved to be biperiodic. So if you notice here, you start in Antarctica, go up to Russia, and then you go into North America, which is what you would expect on the globe as well. So we applied the double Fourier sphere method to the HealPix grid as seen here, and then that allows us to use fast Fourier analysis while still preserving the biperiodicity of the data. So once we have it in this form, we apply, two FFTs, one in the longitude direction, one in the latitude direction, and that gives us a bivariate Fourier expansion, or what we really want is these right here, these bivariate Fourier coefficients. And then once we have those bivariate Fourier coefficients, we're able to plug those into this novel fast spherical harmonic transform, which was proposed by Slavinsky in 2017. So it's a very new method. It was one of the things that made us look into this project. So it very quickly gets us these spherical harmonic coefficients. And in fact, the order of complexity is n log squared n, which is faster than the HealPix method of n to the 3 halves. And again, once we have these spherical harmonic coefficients, that's what we plug in to get the angular power spectrum of a HealPix map. I'm sorry, a CMB map. Okay, so I'm just going to show one of the numerical results from our paper. This is for a test function with which we know the spherical harmonic coefficients, that we can actually calculate errors. Something that we want to note here is that, our method is the dark blue circles, and then various other HealPix methods are shown with the other colors. But this is the same test. This is just on a log scale in L, and then we want to show a more linear scale for high L because, again, as I said at the beginning, the value of the angular power spectrum for CMB maps, what we really care about is the value at high L, the high wavelengths here. So if you see here, on the whole, our method shows better errors for high L. So that led us to conclude that over the consideration of the entire angular power spectrum, that our method showed better results. Now moving on to the second paper, titled A Divergence-Free and Curl-Free Radial Basis Function Partition of Unity Method. We actually just submitted this paper earlier this week to the SIAM Journal on Scientific Computing. And our motivation behind this project is that these divergence-free and curl-free vector fields, again, arise in a lot of different applications. They arise in electromagnetics and compressible fluid dynamics. And so, for example, we have the picture of a wind field on the sphere, which generally they assume to be divergence-free. And oftentimes, especially in geophysics, they'll want to look at vector fields that are tangential to the sphere or a surface in general. So something that we have to remember, or that we have to note here that's important, is that reconstructed vector fields must preserve divergence-free and curl-free properties. This is not necessarily easy to do, but if you want to create an approximate or a reconstruction of the vector field, you have to make sure that that approximate or reconstruction is also divergence-free or curl-free. Now, there have been global methods that are developed for this specifically, and they use radial basis functions, which are the functions that we are specifically interested in this project. So I will be briefly covering scalar RBF interpolation, and then I will cover vector RBF interpolation for divergence-free and curl-free, divergence-free vector fields. So RBFs were developed by R.L. Hardy in the 1970s to solve a problem in cartography. Specifically, if you're given a scattered data set, you want to just find a reconstruction of that surface. So here's just an example with a drainage ditch using RBFs. And one of the biggest pros of RBFs is that the data do not need to be on a grid. The RBFs are actually constructed, and the interpolants are constructed using the data itself. So here to just give you a visualization of what this looks like. So here we have scattered data samples with a function value at those points. And the idea behind RBF interpolation is you take a linear combination of shifts and rotations of this single radial kernel, which we will be calling phi here, little phi. And where the shift comes in is that phi is actually based on the Euclidean distance between points. So taking that phi, you can place this radial kernel centered at each of the sample points, and then you enforce the condition that your interpolant must be equal to your function samples at the points given, and then that will give you an interpolated or reconstructed surface. So this matrix here is positive definite, which means that it gives us a unique result for these coefficients for appropriately chosen radial kernels. Here are some common radial kernels that are used. And here, this epsilon is a shape parameter that determines how peaked or flat the RBFs are. All right, so that was for scalar RBF interpolation. So now, for the sake of brevity, I will just be covering divergence-free vector RBF interpolation here. And then I'll also just cover the divergence-free vector field interpolation of our method. So we have a very similar setup to what we saw before. Here we have a vector field that's sampled at given points. The key idea is very similar, except now we're taking linear combinations of shifts of a matrix valued kernel whose columns are divergence-free. And this kernel is based on the little phi kernel that we saw earlier, and we have to use the gradient and Laplacian operators on it. But with that, again, the setup is very similar. We have a very similar interpolant here. But the nice thing about this setup is that we can actually extract the scalar potential of the vector field. And that's something that's very important to our method. It's something that is going to come up later. So just remember, I'll show this again, but the nice thing about this specific construction and about divergence-free RBFs is that you can, for free, just extract the scalar potential of a vector field. And again, the linear system defined, the coefficients look similar, but now we notice that capital phi div is matrix valued. And in this case, for R2, it is a 2n by 2n system, which is prohibitively slow for very large n. So for our project, we were thinking, okay, well, we really want to utilize the great properties of divergence-free vector RBFs, but we need to find a way to make it applicable to very large problems, the problems that arise in the applications that I spoke of earlier. So now this is where we developed our methods. This is what we did. We developed a divergence-free radial basis function, partition of unity. We also did this for curl-free vector fields in R2 and on the sphere. And then additionally, we also did curl-free fields in R3. All of that is covered in the paper, but again, for the sake of brevity, I will just be covering the divergence-free case in R2. So here's our problem setup. We have these scattered nodes on a domain, what we're going to be calling the star domain, and then the corresponding samples of the vector field on the right, and this vector field is divergence-free. So I've been saying this thing, partition of unity. The nice thing is that in a lot of mathematics, it's very self-explanatory. So the partition of unity, you first take a partition. So the first thing that we want to do is we want to take these patches and put them all over the domain that we have. And we say that the patches form an open cover, which just means that every node in the domain is in at least one patch, and all of the patches are distinct. Then the unity part comes in with these compactly supported weight functions. So we define these weight functions such that when you sum them all together, they exactly equal 1 over the entire domain. This is an example of one of them. This is called the Wendland function. And we use this, and I think both projects, this and the next one. It's a very common one used in literature. And this is, to the right, you can see what this looks like on one patch. It is compactly supported. It's not defined outside of that patch. And so we would make one of those weight functions on every patch. So the way that this partition of unity works in combination with the divergence-free radial basis functions is that we form a divergence-free interpolant on each patch. And then we're able to actually form the global interpolant by blending each of those individual interpolants together with the weight functions. Now, unfortunately, it's not that simple, actually. This global interpolant is not guaranteed to be divergence-free because of this multiplication by the weight functions. So we have to modify our approach slightly. So I said earlier that this scalar potential is going to come back. We realized that this was the way to get that global interpolant to be divergence-free. So again, as I said, once you form that divergence-free interpolant, you can get the scalar potential for free. So we still form the divergence-free interpolant on each patch, and then we extract the potential on each patch. And then what we do is we form a global approximant to the potential by blending the potentials on each patch together using the partition of unity weight functions. But again, it's not that simple. This is the last asterisk here. This is really important. Unfortunately, these scalar potentials are only unique up to a constant. So as you can see here in the picture, you can actually see where the patches were in the domain. It's not smooth. It's not a smooth reconstruction of the potential. So what we have to do is we actually have to adjust each of the potentials by a constant, by a scalar. And then with that adjusted, excuse me, with that adjusted potential, we can blend those together and get the global approximant to the potential as a whole. This is like the crux of the method, and so I wanted to just briefly explain how we do that. How do we get these shifts of the potentials? So here's an example on the right of what these patches look like in a domain. We're going to let these x's be the centers and rho be the radii of the patches. And if two patches overlap, we can actually find the center of the overlapping region using this equation here. It's like an averaging equation. And again, our problem is that we want to find these numbers, values, scalar values, such that they make the potentials in the overlapping regions approximately equal. So we actually use graph theory to solve this problem. So you can kind of see here, these centers are the vertices of the graph, and then the connections here are the edges. So from the graph theory, we're actually able to form the system and solve for these constants. So that's how we solve for the shifts in these potentials. And then now you can see that the recovered potential is nice and smooth. So we do that, we shift the potentials, we blend them together using the partition of unity weight functions. And then from that potential, as you can see up here, we can get the divergence-free interpolant from the potential. So again, just a reminder for the problem that we're looking at the star problem. These are the nodes on the left, the field on the right. Here's our numerical results. Just a couple of notes. This Q that you see in the legend, that's just a parameter that controls the number of points per patch. So you can see that as Q increases, we get better errors. However, if you think about it, when we increase the number of points per patch, we're actually slowly going to the global problem, because eventually, as you have more points in a patch, you have fewer patches. So obviously, you'll get better results as you get more points in a patch, but the whole point is you want to balance cost with approximation power. So here we have the errors for reconstructing the potential on the left and the errors for reconstructing the field on the right. And again, as I said in the paper, we also developed this for problems on the sphere. So here's just a quick example of a divergence-free field on the sphere, and then what the partition of unity patches would look like in that case. And the errors are very similar to the previous ones, but what I really wanted to get to is this wall clock time. Something that's great about this method is that it has a theoretical complexity of n log n. So you can see here it's looking linear. And again, like I said earlier, notice for the largest Q, it's more expensive. So that's the nice thing about this method, though, is that we're able to get good errors and still really good speed. So we're very proud of this method. We're very, very proud of this, these graphs here, these images. Finally, the third paper, Implicit Surface Reconstruction with a Curl-Free Radial Basis Function Partition of Unity Method. So hopefully those last few words sound a bit familiar. It was actually what we just covered. This third paper, this third project, was born while we were working on the second project. And we realized that there's this application that seems to fit very nicely into what we already did in the second project. And it's a problem that arises mostly in computer graphics, but in medical imaging and really across the across all disciplines. So, for example, here we set up the problem with something called a point cloud. So you can kind of see the way it looks. It's a bunch of points that almost look like a cloud, but really they're points that come from a scanned surface. So you see on the left is a point cloud for a mammoth tooth. On the right is a point cloud for a Cantus abditis tooth, which is an Eocene era primate. But anyway, the anthropologists that study these animals, it would be important for them to have a digital representation of these teeth so that they can get ideas about the animal's diets, they can run calculations on it. But in order to do that, you need to actually reconstruct the surface that the point clouds were gathered from. And so that's what we're doing. We wanted to apply our method developed in the second paper to the problem of reconstructing surfaces from point clouds. And we did, and it works very well. So as I said in the title, this project involves curl-free vectors, curl-free vector RBFs. So I covered divergence-free earlier. I'm just going to give you the setup for curl-free vector RBF interpolation. Again, it's very similar. We have this now curl-free vector field here on the right, and now we have this curl-free matrix valued kernel, still based on this little phi here. And the interpolant is formed in a similar way. Excuse me. And then again, as we saw in the previous paper, the scalar potential is important. It's crucial to the method. So we can also extract the scalar potential from the curl-free interpolant. So the setup is the same for the linear system to solve for the coefficients. But something that we that we noticed while we were working on reconstructing some of the surfaces was that the shape parameter that comes up in these phi, if you remember that slide where I kind of showed some commonly used little phis, that shape parameter was a real big pain. And in fact, for a few minutes while we were working on reconstructing some surfaces, it even made it look like our method didn't work because the shape parameter was way off. And we had to spend all this time trying to find an optimal shape parameter, which was a waste, and we just wanted to do away with it. So we did. So we actually ended up using polyharmonic splines. So here's an example of the polyharmonic spline kernel where L is a non-negative number. So the process is very similar and it will look very similar. It's just slightly more complicated. So here's the curl-free polyharmonic spline interpolant. Notice that we still have this, I guess, base interpolant, if you will, but we have to add on these curl-free polynomial basis vectors here. So you add those onto the interpolant and that creates the polyharmonic spline. So again, the setup is very similar. We still impose these constraints on the interpolant that the interpolant is equivalent to the vector field at the sample points, but we also have to impose these additional constraints for the curl-free polynomial basis. And that gives rise to now this system that we have to solve. So really quick, this A curl is what I showed here based on the capital phi curl. Then we also have now the matrix based on these curl-free polynomials. So again, a reminder, we want the scalar potential. And so you can extract the scalar potential of the polyharmonic spline interpolant, the curl-free polyharmonic spline interpolant. Looks similar, but still just more complicated. But this is what we use in our method. So what is our method and why does it work? Even I was thinking, how would curl-free radial basis functions apply to surface reconstruction? Well, we are actually taking advantage of this result from vector calculus that normal vectors to an implicit curve or surface are actually curl-free. So we realized that we can actually fit the normal vectors to a curve or surface with this curl-free radial basis function interpolant, and then we can extract out that scalar potential, and then that scalar potential is what will give us the approximation to the implicit function. So here, just as an example, we have points on a curve with the normal vectors. So we fit the normal vectors with an interpolant, extract out the potential, and then the potential is what approximates, in this case, the implicit curve. Magenta here is our approximation, and I think blue is the exact. Okay, so that's technically the global perspective. It works really well for curves. The global case is fine because n is small, but again, as we saw in the second paper, what if n is really large? So here's still a curve, but just to give you an idea of what the partition of unity would look like. We have all of these points, all of these normal vectors, and so we put a partition of unity over the domain again. And then just as before, the method is the same, obviously. We fit a curl-free interpolant on each of the patches, then extract the potential on each patch. And then we still have to do a shift of each potential, but now because we're reconstructing an implicit function or an implicit surface, we know what the potential has to be. So we just adjust it by its own mean, which ensures that the mean of each potential, the potential on each patch will be 0, which if you can think about it as like pulling the approximant closer to the 0 level curve or surface, which is what we want to reconstruct. Then once we have those potentials, and so now we're not even interested in the global interpolant necessarily, we're just interested in the potential. So we blend that shifted potentials with those partition of unity weight functions, and then that gives us the F, the implicit function or surface that we were wanting. So this is incredibly useful and also necessary when we're thinking of surface reconstruction. Again, as I said, for curves, the global case works fine, but here we have a point cloud of Homer Simpson on the right. And then we also have a point cloud of a dragon on the left. So even for the smallest point cloud that we had access to was Homer Simpson, it's 5,103 points. Even for that, the global case was just way, way too expensive. It just, I couldn't even actually get a result for it on my machine. So, but then you think of the dragon, here only a few of the points are shown just so you can actually see the cloudiness of it, but there's something like 400,000 points for the dragon. So that is literally impossible to do in the global case. So that's why we need this partition of unity to make it faster. So these are our reconstructions of those two examples, and we also did them to others, the armadillo man and the bunny. Some of those are from the Stanford repository. So there's actually a lot of these point clouds and surfaces out there for reconstructing. All right, I just want to conclude this with just kind of reviewing what I covered and what our contributions were. So in the first paper, we contributed the first fast and accurate algorithm that utilizes the fast spherical harmonic transform to compute the angular power spectrum of data collected at the HealPix points. For the second paper, we developed the first method based on divergence-free and curl-free RBFs, as well as the partition of unity for approximating divergence and curl-free vector fields in R2 and on the sphere, and then additionally for curl-free vector fields in R3. Then finally, in the third paper, we developed what we're calling the CFPU method, which is the first to use the curl-free RBF PUM to reconstruct implicit curves and surfaces. Some future work for the first paper is that we would really like to, right now our code is in Julia, we'd like to transcribe it into a lower level language like C so we can get better timing comparisons with HealPix. The HealPix software has been around since the 90s, so it's all in C, it's all very optimized. So we would like to do some of that to try and make it a bit faster, at least like the runtime a bit faster. We also want to include the ability to perform Fourier synthesis on a CMB map, which is just given the coefficients, get the map back from it. I just showed given a map, get the coefficients. That would be really quick to do with our method, so we're really hoping to implement that. And then additionally, add the functionality for analyzing the polarization of CMB maps. It's a bit more of a complicated problem, but it's also of interest to cosmologists, and it's available to us to do, so we want to do that as well. For the second paper, we want to look into using our method as basis for solving numerical PDEs. Again, we talked about like the shape parameter of RBFs. So currently there are algorithms that work with flat RBFs. So we would like to maybe adapt some of those for divergence and curl-free RBFs. That's actually what my master's work was on. And then also we'd like to parallelize the algorithm because it is highly parallelizable for the most part. For the third paper, we would like to adapt the method to use different shapes for the patches. Right now, in 3D, we're just using balls for the patches, so it would be really nice to maybe use like ellipsoids or kind of fit the patches, if you will, to the surface that we're given. We want to investigate other regularization procedures for smoothing noisy data and also find better evaluation metrics. Currently, everyone in the literature just kind of uses the I-norm. So in our paper, we do introduce some convergence rates for our method for known problems, which is nice, but we're hoping to look into like a better way to show how a method performs. Before I conclude, I just want to acknowledge my committee, especially my advisor, Professor Wright, as well as Professor Mead and Dr. Long. And also I would like to thank Dr. Snelson for being here. And thank you to every single one of my family members and friends who are here. It means so much to have your support on this very momentous day. And thank you all for your time.
Thank you very much, Kathryn. At this time, we open the floor to public questions. We'll have a few minutes for any member who's not on the committee to ask questions. It will probably be easiest to unmute your mic to ask those. Kathryn, are you comfortable with chat-based questions as well?
Yes, I can I can do chat based.
Okay.
I
In
believe.
case
I
someone
don't, I
doesn't.
don't actually see the chat in my options.
Oh, you don't have that as an
Right.
option? Maybe it's best just to use microphone then.
Oh, I'm sorry. Luckily, my live audience members showed me where it is. I found the
Okay,
chat.
great. Okay,
I'm doing
well,
a PhD.
I'll mute and let the audience ask questions, and you can answer those until we're finished.
I had a question.
Yes.
So with the first paper, I don't know much about the CMB, but I assume that there's some amount of noise in our measurements. How
Yeah.
sensitive is your algorithm to noise, and how does that compare to other algorithms in noise?
Yes. So we were able to test that with like Gaussian noise on a test problem, and we actually showed very favorably. It did very well with noise, but unfortunately we don't. The CMB maps are collected. There's an entire pipeline with CMB maps. So they collect the data over the course of like 9 years. They compile the maps. They do all of this stuff to it. And then the maps that are available to the public are already like pristined, if you will. So unfortunately, we didn't get to kind of see, how it would deal with like raw data. But we did do noise on a test problem, and it handled it very well.
I have another question, if no one else wants to. So I think in the surface reconstruction, your example were on teeth, which as someone who knows nothing about teeth, I think of them as like sharp things that are not smooth and have cusps. But I think your surface reconstruction, I think, made some assumptions about smoothness, so the results are smooth. Can you say something about that?
Yeah, so not exactly. That was actually why we wanted to use this partition of unity, because RBFs are used a lot in the surface reconstruction literature, but they're usually global methods, or they try to use like compactly supported RBFs. But the nice thing, and actually the huge advantage to doing a partition of unity, is that we're actually solving the problem locally. So we actually really pick up on these sharp features. So I'm not sure if you can, sorry, going back now to the dragon, like you can see we get even the scales, we get the sharpness of the teeth, like we really, and what I was saying about smoothness is that we have a parameter that we can adjust to make something more smooth. So we could flatten these out if we wanted to, but if you wanted to really get these sharp, finer details, I mean, even you can look at the feet here. That's the nice thing about our method. It is local, so it picks up any sharp features that are actually native to the surface.
I had a question.
I've got a question.
I'll go first. With regard to parallelizing the algorithms, is a lot of that gained because of the partition of unity methods, or is that within a different part of the algorithms?
Yeah, the partition of unity part, because really right now, in like serial, is that what it's called in serial when it's not parallel?
Yes.
You just, yeah, thank you. So what we're doing is literally forming the interpolant on each patch, just like in iteration. So like one patch, do the interpolant, next patch, do the interpolant. So the only thing that's not parallelizable is when we have to do that shift of the potentials, because you need like the data to talk to each other. You need to know where the patches overlap and what the data is. But that part of, and it is the slowest part actually, is forming the interpolant on each patch. That is completely parallelizable. And so that would be something we would do next.
Cool. Thank you.
Mm-hmm. Who was the other question?
Oh, that actually was in vein with my question, was about the parallelability of the function. I know that there's a lot of demand in the mobile space right now for reconstructing surfaces from dots acquired on mobile devices. Yeah, it was something that even the Navy was working on in my internship last year. It's a big thing. So yeah, it's highly parallelizable. So that's like the next step before we publish the paper. We want to do that.
Can you go to the first map?
I'm sorry, which map?
With the CMB?
Oh, yeah. Oh, wait. My MacBook has the, ooh, this is so cool. The touch bar has a slide option. Look at that right away. We love it. Okay. Yes.
Do you like know that like where it has more like the red pockets versus the blue pockets, like what that corresponds to, or?
Yes, yeah. So these are the differences in temperature. So the red parts are where there's like a higher difference, so like a hotter, if you will, temperature, and then the blue parts are where they're more similar, so like a smaller difference. Gotcha. So it's a map of the temperature differences, because if we were to map the actual temperature, it would just be one color, because that's what I was talking about, where it's a black body. It's like completely uniform in temperature, and there's like these really, really small temperature differences, again, like on 1 part in 10,000. So that's what we're interested in, so that's what the maps are of, because otherwise the maps would be terribly uninteresting.
Okay, cool.
Mm-hmm.
Are there any additional questions from the public? Okay, if we have no further questions at this, do we have something else? I'm sorry. Okay, I guess.
I don't believe so. I believe the next step is the private interrogation.
Perfect. At this time, we're going to ask the public audience to leave the meeting so that we just have Kathryn and the committee. And thank you so much for attending.
Yes, thank you all so much for being here. I really appreciate it.
Good job.
Thank you.